Okay, welcome back everyone. We have now finished this overlong chapter on the Schwarzschild black holes, and we will begin now with a new chapter which will be not quite as long. This will be about spherically symmetric gravitational collapse. So we will really be concerned with the dynamical process of an object collapsing. And what we will do mainly, apart from some other more qualitative discussions, is that we will calculate the collapse of a ball of dust. That's what Oppenheimer and Snyder did in their famous 1939 paper, and which can be found in many books. Okay, so we have been talking about the Schwarzschild metric, which is static. So there's no time dependence, so it describes black holes. But these black holes exist forever, from t minus infinity to t equal plus infinity. So what we actually expect to find in nature is black holes which have come into existence at some time. So where we had a star, an ordinary star, and then at some instant the star became unstable, and then it collapsed into a black hole. And that's the process we want to discuss now. So let me begin with a few general remarks what might happen with a star if it becomes unstable. So an ordinary star like our Sun is stable. Why is it stable? There are two forces which balance each other. There's a gravitational force which wants to contract the whole thing, and then there's a pressure which wants to push it outward. And for the long lifetime of stable stars, these two forces balance each other. But then, when the fuel, the nuclear fuel in the core of the star has burned out, then this balance is perturbed. And what happens is that the star becomes irregular. It will erupt. It will blow away a certain amount of its mass. And the question is, can it, after this period, can it settle down into a stable state at a radius which is bigger than the Schwarzschild radius? And this was a question which was seriously discussed since the 1930s. And it began with the famous work of Chandrasekhar, which won him the Nobel Prize. So he found that a possible final state for a star, so let me write here, possible final states. For stars, that a possible final state is what we call a white dwarf, but that this is possible only if the mass of the thing is not bigger than a certain limit, which is called the Chandrasekhar limit, which is something like 1.4 solar masses. So the mass of the thing must be smaller, or approximately 1.4 solar masses. By the way, he was 19 years of age when he did this work. That's what won him the Nobel Prize. Actually, he was a little bit disappointed when he read the text of the Nobel the reason why he got the Nobel Prize. This was in the 1980s, so it was much later, because it referred to this very early work. And in his own opinion, what he did in later years was at least equally important. So he was a little bit disappointed that this work from his very early use, that this was considered to be the most important thing he did in his life. But anyway, I think he has no reason to complain about getting the Nobel Prize. So this was in 1934 or 33 or something like that, when this famous paper was published, where this limit appeared. And the question is, what happens with stars which are heavier than this? The state of the matter in white dwarfs is what is called degenerate Fermi gas. So the essential thing is that electrons are fermions. So in a star we don't have atoms. Yeah? In an ordinary star like the Sun, what we have is a plasma. So it's electrons and nuclei separated from each other. And this final state, what we call a white dwarf, is a state where the electrons form a so-called degenerate Fermi gas. So this is something which can only be done by fermions, because the Pauli principle plays an important role for this. And this provides a stable final state for the star. So they have something like 1.4 solar masses or less, and they have a radius of something like 5,000 kilometers. That's about the size of the Earth. Yeah, Earth is 6,000 something kilometers, I think, the radius. So that's one possible end state. So what happens with a star that is heavier? There's another possible final state, which is called a neutron star. This is, well, very figuratively speaking, what happens is that the electrons are pushed into the protons to form neutrons. Yeah, but don't take this too literal. This is very, very oversimplified. It's a picture for popular explanations. So the matter then consists essentially of neutrons, and there is also, but for this there's also a final mass limit, which it's much more difficult to calculate, and actually it's not clear until now where exactly this mass limit is. We know neutron stars of up to 2 solar masses. Recently there was the first neutron star with more than 2 solar masses found, a little bit more than 2. And where speculations go in the direction that maybe 2.5 or 3.5 solar masses might be something like a limit. Some people go further up, but certainly not beyond 10 solar masses. So there's no question that there is a final mass. Why is this so difficult? Well, because the matter models are much more complicated. In particular, if the thing is rotating, then it's really difficult to get a final, to get a bound for the mass, and that's the reason why we don't know exactly what's the maximum mass a neutron star can have, but it's certainly not more than, say, 10 solar masses or something like that. And we know stars which have considerably more mass than 10 solar masses. We also know compact objects, which we actually believe to be black holes, which have masses considerably more than 10 solar masses. So the famous solar black holes, stellar black holes, I mean, the most famous candidate, Cygnus X1, has something like 15 solar masses. Yeah, we know the mass pretty well. So whatever it is, it's certainly not a neutron star. So yeah, if now we have an object which is even heavier than this, then the idea is then that it must end up as a black hole. Yeah. So there is no final state which can stop it. There are hypothetical objects here in between, something which is called a quark star, for instance, but they are highly hypothetical, and they also have certainly mass limits, so they cannot exist for arbitrarily high masses. So the idea is that there is a certain mass. If a star doesn't manage to blow away sufficiently much mass in order to get under this limit, then it must end up as a black hole. And what we want to discuss now is how this process takes place, where the star starts as with a finite radius bigger than the Schwarzschild radius, and then it collapses under the influence of its own gravity. Well, what we can say quite generally is how this would look for a spherically symmetric star in an Eddington-Finkelstein diagram. So I think I had called this coordinate t twiddle. This was the Eddington-Finkelstein time. Here we have the horizon, Rs, and now we have a star which begins with a radius bigger than the Schwarzschild radius. And now we don't know, from what we have discussed until now, we have no idea how this process of collapsing exactly takes place, but whenever the surface of the star has crossed this horizon at r equal Rs, then the star is doomed. From then onward, it must collapse in a finite time to the singularity here at r equals 0. And we even calculated this time. Here's the maximum value for this time. The argument is, of course, that so this region is not, in this region the Schwarzschild metric is not valid. The vacuum Schwarzschild metric is only valid in this part. But the surface of the star is certainly formed out of matter volume elements which have to move at the subluminal speed. Yeah? And because they border on the vacuum spacetime, they have to move at time-like curves in this vacuum spacetime. And time-like curves in this vacuum spacetime have to go to the singularity. So we know whenever it has crossed the horizon, then the star must collapse to a singularity. And of course, I would like to calculate this process explicitly. So I would like to start with a meta model for the interior of the star and then calculate this dynamical process explicitly. And in analytical terms, this is possible only for the highly idealized case of a ball of dust, if there's no pressure whatsoever. So you may ask yourself, well, that's not particularly intriguing. If I have a ball of dust, what else should it do? Instead of collapsing to a point, if there's no pressure, which balances this. What makes this solution interesting is that it is an exact solution to Einstein's field equation, which can be written down analytically. You can write down the metric, we will do this. You can write down the density, you can write down the time which it takes the object to collapse, you can write down everything explicitly. And for this reason, I think it's worth discussing this. So what we now want to do is collapse of a spherical, or let's say of a ball of dust. Let's put it this way. Yeah, spherical. Spherical ball of dust. A ball of dust could also rotate, right? When I say spherical, it's clear that it does not rotate. It's spherically symmetric of a spherical ball of dust. So we start, of course, with a radius which is bigger than the Schwarzschild radius. So here we have dust. So what we will have to do is we have to solve Einstein's field equation for a dust, for the interior. In the exterior vacuum, we know the solution already. This must be Schwarzschild. Even if the thing in the middle is time dependent, as long as it is spherically symmetric, we still have Schwarzschild. And then, so we put this ball in a certain initial state, and then we let it go. And under the influence of its gravity, it will collapse. So at a later stage, it will be smaller, and the matter will be moving inward. And at some final time, we will have a point in the middle. So at some stage, the horizon will form. Here in this situation, there is no horizon, because the Schwarzschild metric is valid only outside of the star, and this doesn't extend down to r equal rs. But then at some stage, the horizon will form, and finally the thing will collapse to a point. So this is at the time t initial, and this is at the time t final. And this is a finite time interval. That's what we want to calculate. Okay, because we assume spherical symmetry, we will start with an ansatz for the metric that it is spherically symmetric. So, spherically symmetric. Metric, we will write this in coordinates as usual. Spherical polar coordinates, so we have a time coordinate, which I denote t. Then we have a radius coordinate, which one usually would denote r, but for some reason I will denote it rho, because this coordinate will not be the standard Schwarzschild coordinate when we match the two things at the boundary. And because we used in the preceding section r for the Schwarzschild coordinate, for the area coordinate, which gives the surface of an area, I think this might cause confusion if I would call this coordinate here also r, so I call it rho. And then I have the angular coordinates theta and phi. And the general form of a spherically symmetric metric, I hope everybody has seen it before. So I think wherever you have heard about general relativity for the first time, when the Schwarzschild metric was derived, certainly one started with a general form of a spherically symmetric metric. And this can be written in this form, c squared minus c squared e to the nu. And there's a function which depends on the time coordinate and the radius coordinate, which I now call rho, then dt squared, then a coefficient of the dr squared, which I call e to the lambda, So I write them in the form e to the something to make sure that they have the right sign. Yeah? This is supposed to become a time-like coordinate, so I want to have something negative here. And if I write the coefficient in this form, then this is guaranteed. And similarly, I want to have this positive. And then I have something in front of the angular part. So the angular part is d theta squared, the sine squared theta d phi squared. And what we have in front of this can be made equal to the to the radius coordinate. Yeah, when we worked out the Schwarzschild solution, actually we did this. We had just a rho squared here in front of this. This can always be done by an appropriate choice of the coordinate. Actually, there's a subtlety. A certain derivative is not allowed to be zero. So there are exceptional cases where it does not work, but generically it does work that we make this equal to rho squared. But in this particular case, for discussing this problem, it's not convenient to do this, and for this reason I leave something else here, which may be an arbitrary function of t and rho. I call it y. So just to remind you, when you start discussing spherically symmetric metrics, and you want to write down the most general form of such a metric, you also have a cross term, dt d rho. This would also be an agreement with spherical symmetry, but then you make a coordinate transformation to kill this term. Yeah? So you make a coordinate transformation which mix your old t and your old rho in a certain way, and then you end up with a new t and a new rho where the metric is diagonal. So this is always possible. And now, as we want to discuss this problem of a collapsing ball of dust, it will be convenient to choose the t-lines in such a way that the dust follows these t-lines. Yeah, so that the t-lines are the world lines of the dust particles. And then this cannot be done simultaneously with having this equal to rho squared, and that's the reason why I leave this general. So we want to consider a dust. So what we have done is we have solved for this general form of the metric the field equation for vacuum. Yeah, this gives Schwarzschild without a cosmological constant. I think most of you have also seen the solution for spherically symmetric metric with a perfect fluid with constant density. That's what one calls the interior Schwarzschild solution. Yeah, in my GR course, I also discussed this solution. This would give a static star, which of course must have a pressure. Without pressure, it cannot be static. Yeah? So that's, I think, something also many of you have seen before. But what we discuss now is something which is not static, and where the source is a dust. So the energy momentum tensor is, wait a minute, we have nu and lambda and rho already. I should use indices which cannot be confused with this. What Greek letters are, let me just call this beta and gamma. So for a dust, let me write the one with the upper indices. For a dust, I hope everybody remembers, this is a mass density times the 4 velocity, u beta, u gamma. Yeah? We have a dust, the dust has a density, rest mass density, that's the mu, and it has a 4 velocity. Yeah? The flow lines of the dust, that's what I call u beta. And as we usually do, we normalize this in such a way that the parameter, yeah, u is something like dx by d tau, that the parameter is a proper time along the world line. So this is supposed to be normalized. And we want to choose our coordinate in such a way that the u is parallel to d by dt. So I think I can squeeze this here. So u is supposed to be a factor which we have to determine times d, oh, let me write it in this way, d by dt. So yeah, if you prefer to work to read this in coordinates, so we have, let me write it again. We have written u is alpha d by dt. So if you want to write this as u alpha d by dx alpha, then you compare the, maybe I should, because this is alpha, should use a different letter here. If you compare coefficients and you see that your u beta is something like Kronecker delta beta t, and what's the coefficient? U beta is alpha delta beta t, okay? And we have to determine alpha. And alpha is determined by the normalization condition. we want to have GUU equal minus c squared. So u is supposed really to be the 4 velocity of our dust. If I insert this expression here, I get alpha squared g d by dt d by dt. And this is just the coefficient gtt, right? And I can read this from our metric ansatz. GTT is what we have in front of the dt squared. So this is minus c squared e to the nu. Okay. Oops. So if I compare this expression with this expression, then I find, I forgot the alpha. So this implies that alpha is what? We want to have it positive. Yeah, the 4 velocity should point in the direction of in which t is increasing. So alpha is e to the minus nu half, right? And this means our 4 velocity u is e to the minus nu half d by dt. Okay, so that's what one calls no, not yet. I wanted to say this is what one calls co-moving coordinate, but not quite yet. We make a little coordinate transformation now. So let's insert this expression. There's one thing I left out the arguments, but nu is a function of t and rho, right? Nu is a function of t and rho by this ansatz. But now we have a dust, and a dust moves on geodesics. So this u, this vector field u, must be geodesic. And my claim is, I will prove this in a minute, that if this vector field is geodesic, then this coefficient cannot depend on rho. It can depend only on t. So my claim is, or let me first write just as a recollection, that from our assumption that we have a dust, there's the energy momentum tensor. For dust, I hope everybody remembers that this equation, which follows from the field equation, yeah? Remember, this is, well, it's a local version of energy conservation. That this is a consequence of the field equation. We want to solve the field equation with this energy momentum tensor, and then the energy momentum tensor must satisfy this. But now we have a dust, and if this is a dust, then from this equation we find that the vector field u must be geodesic. So this implies that del u is 0. So in the GR course we did, we evaluated this expression for a perfect fluid with arbitrary pressure. And then we got the Euler equation. Yeah, and the Euler equation simplifies to this equation if the pressure is 0. Yeah? So I will not repeat this now here. So I assume that we know this. So if we have a dust, then the 4 velocity of the dust must satisfy this geodesic equation. And from this, I claim that one can prove that this coefficient nu, which is a function of rho and t by our ansatz, is actually independent of rho. And the proof runs in the following way. Well, if del u is 0, then certainly this expression is 0. D by d rho. Yeah? If I plug a 0 in one slot of the metric, then of course the whole thing is 0. And this can be rewritten now. Remember, this is a Levi-Civita derivative. So I can use the compatibility of the Levi-Civita derivative with the metric. By the way, you can do this in 2 different ways. A more down-to-earth way of proving this would just to write this out with the Christoffel symbols. Yeah? Then you would get the same result which I get now. But I think it might be instructive to demonstrate how to do this in invariant notation without using the Christoffel symbols. Yeah? So if you prefer a more elementary way of calculating is just express this expression with the help of the Christoffel symbols. For this type of metric, you have to calculate it, of course, for this metric first. Yeah? And then you will get the same result. But I'd show you a different proof here. So this would be with a compatibility rule between the Levi-Civita derivative and the metric. So that's a kind of product rule, right? So I can take this derivative out of the whole thing. It's compatible with the metric, so the derivative of the metric gives nothing, and then I get the derivative of this term here, d by d rho. So that's the same thing. So this is to be read in the following way. This is a scalar function. Yeah, vector field inserted into metric gives a scalar function, and this vector field applied as a derivative operator to this function. Okay, now let's insert our expression for u. So u is e to the minus mu half d by dt. And here I can take the e to the minus mu half out of the bracket. And then I have what? I have g d by dt d by d rho. And here it is the covariant derivative is linear in this entrance, so I can take the factor e to the minus mu half out of both terms, minus e to the, let me write it in this way, so that you see I pulled it out of both expressions. And then I have g d by dt del d by dt d by d rho. Okay, okay, let me write it again. Oops. So I continue here. This is e to the minus mu half d by dt e to the minus mu half, and this is just gt rho. And then minus e to the minus nu g d by dt. And because our connection is torsion free, I can interchange these two things. Yeah? If I interchange them, I would get the Lie bracket, but the two partial derivatives commute. So the Lie bracket is 0. So this is the same as the two things in the other order, d by d rho d by dt. Okay, and this here, if you look at the expression for the metric, there's no cross term, no t rho term, so this is 0. Okay? And so the first term is gone. What do we do with the second term? We use again the compatibility of the derivative and the metric. So if I use the same kind of product rule, I get 1/2 d by d rho g d by dt d by dt. Yeah? If you calculate this expression, you get once the derivative of this term and once the derivative of this term. But because the metric is symmetric, this gives 2 times the same term. The 2 cancels against this, and then I end up with this here. And here I have GTT. And GTT was what? E to the minus nu 1/2 d by d rho. GTT is down there. This was minus c squared e to the nu. Minus c squared e to the nu. Okay, can we simplify it a little bit? This gives c squared half. E to the minus nu and e to the nu cancel, and I have just d nu by d rho. And on the other side of the equation, I have a 0. And that's what I wanted to prove. Yeah? That nu must be independent of rho. So this was this little proof. So yeah, it might be useful to know that you can do calculations of this sort without actually calculating the Christoffel symbols. But in this case, it doesn't save us much time, because later, when we want to evaluate the field equations, then we have to calculate the Christoffel symbols, so we need them anyway. But if this would have been the only goal, then we could have done this without knowing the Christoffel symbols. So the metric reads, it's simplified now. So in the beginning, we had here a factor e to the nu which depended on t and on rho, but actually now it depends only on t. And then we have dt squared plus e to the lambda. This is still dependent on both things. d rho squared plus y of t and rho squared d theta squared plus sine squared theta d phi squared. And now you see, if you have a factor in front of the dt, which is just a function of t, you can combine this into the differential of a new time coordinate. Yeah, as long as a rho is here in it, this of course doesn't work, because then you would have to use the chain rule and you would get cross terms and you would mess up the whole thing. But if this depends only on t, then you can introduce a new time coordinate. New time coordinate. So we transform only the time coordinate. We leave everything else as it was. Yeah, so we transform from t, rho, theta, and phi to tau, rho, theta, and phi, where only the t is transformed in the tau. And well, it's done in such a way that this becomes d tau squared. So d tau is supposed to be e to the nu of t half dt. Yeah? If you like, you can integrate this. So you can write, well, if you want to write it quite pedantically, and you would write e to the nu of t tilde half dt tilde, you would start at some integration constant and integrate up to t. Yeah, it's a transformation from t to tau. If you differentiate this, if you differentiate with respect to the upper limit, then you get the integrand at the point t times dt, exactly this here. Oops. And then, of course, this term is just the d tau squared, and that's what one calls the spherically symmetric metric for a dust in co-moving coordinates. Actually, it also works for a perfect fluid. Yeah? I've proven this here only for a dust. I've assumed that the geodesic equation holds for the flow lines. If you use the Euler equation, if you have a pressure term, the argument also works. You can also introduce these co-moving coordinates for a perfect fluid with non-vanishing pressure. And that's what usually is done if you work with perfect fluids under the assumption of spherical symmetry. So the metric reads now what? And that's the form of the metric which we'll use for solving the field equation. We have just minus c squared d tau squared, and then e to the lambda rho of t d rho squared plus y of rho, or I wrote it in the other way around, d theta squared sine squared theta d phi squared. So this is what is called spherically symmetric dust in co-moving coordinates. So if you want to have this equal to rho squared, you could also do it, but then it would spoil this here. Yeah, you cannot have both things simultaneously. You have to make your choice. Okay, so what are the flow lines of the dust now? I should write this down. So u in our old coordinates was e to the minus nu half d by dt, right? And now we have the transformation between t and tau. Oops. Yeah, I have this here. And yeah, if you rewrite this in terms of the partial derivatives, which are just the inverse, so d by dt is e to the nu of t half d by d tau, right? D by d tau. So I insert for t this expression. Wait a minute, is it? Yeah, it's plus, right? It's plus d by dt. And here I have a minus. Very good, very good. So this was e to the plus nu half d by d tau. So it's just d by d tau. Yeah? So why do I denote this coordinate tau? Well, because it's proper time along the flow lines of the particles. Yeah? That's what this equation says. Yeah? Because here the factor is just minus c squared. This means tau is proper time along the tau lines. Okay, and the energy momentum tensor is now this was T alpha beta, mass density times U alpha U beta, and this is now just the Kronecker alpha tau, right? If I use the coordinates tau, rho, theta, and phi, then this is just the Kronecker alpha tau. So this is not an index tau, it refers to the coordinate tau. So you could write a 0 here. Yeah, if you call tau x naught, then you could write delta alpha naught. So these are the things with the upper indices. Let me just remind you, if for some reason you would like to work with the things which have the indices down, and of course I would have to pull down both indices with a metric, and I would end up with the alpha tau, the beta tau. Yeah? So you can also write it in this way. And the nice thing is, if you look at this expression here, you see, and now you let run alpha beta over all possible values. So it takes the values tau, rho, theta, phi. Then you see that out of these 4 times 4 numbers, only one is different from 0, namely the tau-tau component. Yeah? So this 4-4 matrix, which gives the energy momentum tensor, has only one element which is different from 0. So that's the advantage when you work in co-moving coordinates. Yeah? If you had worked in other coordinates, then you would have more non-zero components of the energy momentum tensor. Okay, this was the preparation. Now we have to write down the field equation. So have to solve field equation. R mu nu minus R half G mu nu. So here we have to insert our form of the metric, this form of the metric, into these expressions. And on the right hand side we have kappa T R. Now I wrote mu and nu. Hope that's not too confusing. So now they are just coordinate indices. Is there a question?
I just don't understand the second equation of the moment.
This here?
Yes.
Okay. What was our rule for pulling indices? So quite generally, how is T alpha beta associated with T, say, gamma delta? So I have to pull down the gamma with a metric. So I need a gamma alpha. Yeah, then it becomes this. And I have to pull down the delta to become a beta. Okay? Oops. And now I insert for this here the expression which I had there. G gamma alpha, G delta beta. So this was mu, delta, gamma tau, delta tau. Oh my goodness. I should use different letter. But I hope you don't confuse the index delta with a Kronecker. And what is the Kronecker doing? If you have a summation, look at this term here. G delta beta delta tau. So you have a summation over delta. So only one of these terms in the sum is different from 0. Namely the one when delta takes the value tau. So it picks out the term where the delta is tau. So from this term you get G tau beta. And the same with this sum here. So if we sum over gamma, only the term when gamma is tau is different from 0, and then this here gives a 1, so we have g tau gamma times mu. And I hope that's what I've written there. Yes, I think it is. Yeah. It doesn't matter if the tau is the first or the second index, because the metric is symmetric, of course. Yeah. Okay. Good. What was I talking about here? We want to solve the field equation. So here on the left-hand side, we have to plug in this ansatz for the metric, and on the right-hand side, we use this form of the metric. We can also raise the indices, and we would use this expression. And yeah, this is something that has to be done. Yeah? So now the calculation starts, and this is actually when Oppenheimer and Snyder did this calculation, they were the persons who calculated this collapse first in 39. They were in the lucky situation that this case of the field equation was already solved. It had been done by Richard Tolman 4 or 5 years before. So they could just take the solution from the Tolman paper and adapt it to their case. So what Tolman had found in 34, I think, was a general solution to this equation under the assumption of spherical symmetry for a dust source. So this is called the Tolman solution of the field equation. Many of you might know it from cosmology. Yeah, if you know what the Friedmann solutions are, the Tolman solutions are special Friedmann solutions. For a constant density. Here at the moment we have not said that the density is constant. Okay, so what do we have to do? Well, the right-hand side is already there explicitly, but the left-hand side, that's where we have to do a lot of work now. I'm not sure, let me see. I won't do this today. I don't want to do anything about this today. I will do this on Tuesday. So what we have to do is we have to calculate for this metric the Christoffel symbols. From the Christoffel symbols, the curvature tensor. And then we have to write all components of the field equation. In general, these are 10 components. Yeah? So this is a 4x4 matrix. It's symmetric. So it has 4 on the diagonal, 6 in the upper right-hand corner. 4 plus 6 is 10. So we have 10 equations for how many functions? We don't have so many functions, actually. We have only 2 functions, the lambda and the y, and the mu on the right-hand side. Yeah? These are our unknown functions. And as you might expect, of these many equations, quite a lot are actually trivial. Yeah? So these are not 10 independent equations. Actually, we will find 4 independent equations. And so we will have a couple of integration constants turning up, which are actually integration functions. And then we get a general expression for the solution in terms of these functions. So if we do this, well, when we did the Schwarzschild solution, actually I calculated the gammas by hand. I showed you how to do this. If you want to do it by hand, I would always do it via the geodesic equation. Yeah, I would write down the Lagrangian for the geodesics and compare coefficients with the geodesic equation and read the gammas from this. Usually we don't do this by hand. If you have done it, say 2 or 3 times in your life by hand, you know how it works, and then you let a computer do it for you. There are many algebraic computing programs which do it for you. You can easily write down a little program yourself with Mathematica, for instance. So I have on my computer a little notebook, Mathematica notebook, to calculate the gammas, which I've written in a few lines. And whenever I need them for a metric, I let the computer do this for me. If we have the gammas, we do the same thing with a curvature tensor, with the Ricci and the scalar curvature. And so I will not do this here on the board. So I will just write down the non-trivial field equations on the board. But I won't do this today because these are 4 partial differential equations coupled, which would fill about half of the board. And if I had written them down, then the hour would be out. So what we do next time is we write down these equations. So only in one expression we have a non-zero term on the right-hand side, yeah? In the tau-tau components. For all other expressions we have the 0 on the right-hand side, but in one component we have something different. And then we end up with a system of partial differential equations for these functions lambda and y, and we have to solve this. We will do this next time. And then we will adapt it to the situation we are actually interested in. This is just an arbitrary spherically symmetric dust solution. And then we will adapt it to the situation where we have an initial condition where the star is at rest, then it collapses, and we will in particular calculate the time which it takes for the whole ball to collapse into a point. But we will do this on Monday. And if you are interested in reading the details, so as I said, this was done by Oppenheimer and Snyder in 1939. The paper is very well readable. It's a very nice and understandable paper. And also the discussion is actually very deep. So at this time, I think there are not many papers from this time where also the geometric discussion of a solution is so well written and comparatively easily understandable. By the way, in this paper they also calculate these things which we did last time, what we now call the shadow of a black hole, and which Singh calls the escape cones. So they also calculated the escape cones for an observer on the surface of the star. Yeah? And as it becomes narrower and narrower if the horizon is approached. So in a sense, one might say the first paper where the shadow of a black hole is at least implicitly mentioned is this Oppenheimer-Snyder paper. Okay, but our task is now to solve this differential equation, and we will do this on Tuesday. And now we have time for the tutorials. Okay, so I say goodbye to everybody who is watching, and we are now doing the tutorials among ourselves.